Let's try to understand how to use antilog table with this example. Antilog of 0.0899. We first split up the number into two parts, first, the whole number, and second, the fraction. Since this number has only fraction, we will split it as 0 plus 0.0899. The whole number is the characteristic, and the fraction part is the mantissa. The characteristic value then goes to 10 to power, which is then multiplied to mantissa. Now to find the antilog, we must find the value of mantissa from antilog table, and multiply it to 10 to the power of characteristic. The antilog table looks a lot similar to the log table. One big significant difference we can see between the log and antilog tables is that the antilog table starts its leftmost column with 0, and log table with 10. So, to find the antilog of 0.0899, we first find the first three digits on the leftmost column, and stick to that entire row. Then we find the fourth digit on the topmost row, and stick to that entire column, and see where do the rows and column intersect. In this case, they intersect at 1227. And since there is a fifth digit also, we get to see the mean difference table of antilog table. We stick to the same row on antilog table, and the column of the fifth digit column, and see where they intersect. In this case, they meet at 3. Let us zoom in for a better look at where they intersect. Now what we do with this 3 is we add it to 1227, and get 1230. This is what we get from the antilog table. But before we progress ahead, we must do one extremely important thing. We add a decimal after the first digit. In this case, we add the decimal after 1, so we have 1.230. Always remember, when you find a value from antilog table, add a decimal after its first digit. If you don't, it might make a baby bunny cry. Now all we have left to do is to multiply the 10 to power characteristic to the 1.230 we found from the antilog table. 10 power 0 is 1, and 1 times 1.230 is 1.23, so the antilog of 0.0899 is 1.23. For our next example, we have antilog of 2.0899. As usual, we split this as a whole number and fraction, like this. Here 2 is the characteristic, and 0.0899 is mantissa. Applying any log to characteristic will yield 10 to power 2. An antilog of 0.0899 is 1.230, as we found in the previous problem. Now we just multiply 1.23 to 10 to power 2, and get the answer to antilog of 2.0899 as 123. The next number for us to convert using antilog is 3.0913. As usual, we separate the whole number and fraction. 3 plus 0.0913, 3 is characteristic, and 0.0913 is mantissa. 3 goes as 10 power, and 0.0913, we need to find this on the antilog table. We need to find the first 3 digit on the leftmost column. Hold that entire row of that number, and then take the fourth digit on the topmost row, hold that entire column, and we see where do these row and column intersect each other. In this case, they intersect at 1233, and since we have a fifth digit we must also use the mean difference table. We stick to the same row in our antilog table, and select the column of the digit on the topmost row in the mean difference table. And they intersect at 1. Let's zoom in for a better visual. We add both 1233 and 1, and get 1234, and do not forget to add a decimal after the first digit, so what we found from the antilog table is 1.234. And lastly, we multiply 1.234 with 10 to power 3, and get 1234, as answer to antilog of 3.0913. The next number for us to convert using antilog is 2.9087. That's not all, this one has a bar over it, meaning it is a negative number. So we will split it up something like this, -2, and -0.9087. And doing this will be absolutely incorrect. The splitting of numbers is a bit tricky thing to do. when we deal with a number that has a bar over it. The key element to remember here is that we always want a positive mantissa to solve. So to make the mantissa positive we add 1 to it, and to compensate for the change we also subtract 1, the negative 1 will go along the characteristic. And we get -3 as characteristic, and plus 0.0913 as mantissa. Now we can move forward and find the mantissa of 0.0913 on any log table, which we did in the previous problem, and get 1.234. Lastly, we multiply 10 to power -3 to 1.234, and get 0.001234 as answer. Next up is antilog of -6.0913. We won't treat this question the same way. We treated a number with a bar over it. We just need to take the negative sign outside the whole operation, and keep it there, and solve the antilog, just as we would solve the antilog of a positive number. So we take the negative sign outside the antilog function, and split the number in whole number, which is 6 here, and fraction, which is 0.0913. Next, we find the value of mantissa from antilog table, which we've calculated in the previous problem, which came out as 1.234. And then we multiply -10 to power 6 to this, and get our final answer as -1234000. Now let's revise the entire process of how we undo the log effect and regain the original value from using antilog. This will give us a good overview of everything, and probably help us understand antilog better. To the left side we write down some values, which we will convert using antilog table. Now we separate the value into two parts, the whole number, which is characteristic, and the fraction, that is the mantissa. We do it accordingly to every value, except for these last two values, which have a bar over them, and that requires a different way of splitting. Now that splitting is taken care of, we now find the value of mantissa on the antilog table. Next, we multiply the 10 to power characteristic value to the mantissa, and get our final answer. So let's now go over the algorithm of antilog. First, we need to separate the characteristic and mantissa. Remember to add and subtract 1, if the number has a bar over it. Then find the antilog of mantissa, on antilog table. Add the mean difference, if needed. And please, for the love of God, do not forget to place decimal after the first digit. Then, whatever we get from antilog of mantissa, we multiply it with 10 to power characteristic, to get the original value, which was the number before we applied log to it. But we won't get the original value every time. And why does that happen? We'll be clear in just a moment. Now let's take a big recap. We took a number 1.23 and applied log to base 10 to it, and find its log value as 0.0899. We used the log table to do this. And then we applied antilog to 0.0899 and resurfaced the original value, 1.23. And we see the same results with 123, 1234, 12.34, and 0.001234. and we get the same results with negative numbers also. If you're paying attention closely, then you may have noticed that 1, 2, 3, 4, 5, 6, 7 was the only number that failed to regain its value back. What we did got back was 1, 2, 3, 4, 0, 0, 0. Only first 4 digits were intact, rest were turned to zeros. This type of error happens only because of the limitations of log table and its dependency on the first 4 digits. The rounding off of numbers is where the problem is, and we have to do this rounding off anyway because we have no use for more than 4 digits in log table. Some more examples of how numbers regained after applying log can differ from the original number. 1, 2, 3, 4, 5 will return as 1, 2, 3, 4, 0. 0.00023456 will return as 0.00023450. And 23.12567 will return as 23.12000. Apart from the problem of not regaining the numbers having more than 4 non-zero digits, the log table is also not 100% accurate in some cases. Meaning, when we use log table to solve complex operations, the answers we get can sometimes vary from the expected answer, even when we properly follow the log and antilog algorithm. That is why the exams that ban calculators and rely on log tables have a 3% error window, which means the examiner will accept the answer, even if the answer we give is 97% close to the original answer. These limitations and disadvantages of log are however only confined to log and antilog tables. If we solve log using a calculator, we won't encounter such problems.